Thank you, Viridiana. First of all, I would like to present our research team. Diego Calderón and Álvaro Opaso are undergraduate students at Universidad Santa María. Constanza Carrasco and Christopher Lorca are master students. Felipe Toledo and Facundo Díaz, undergraduate students at Universidad Católica de Chile. And finally, Claudio Gelmi is an academic in Universidad Católica de Chile that guides the work of Facundo. This presentation will be divided in 4 parts. Firstly, I'll provide a background on supercritical extraction of solid substrates. Secondly, I'll present the mass transfer models that we adopt in this work. Thirdly, my colleague José Manuel will present most studies considering non-idealities in the supercritical CO2 extraction of solid substrates. Finally, we'll finish with concluding remarks. This figure presents the temperature pressure projection for pure CO2. The liquid vapor saturation line ends in the critical point of CO2 that is close to 31 degrees Celsius and 74 bar. When heating liquid at low pressure, below the critical point, we reach the boiling point when we generate a low density and low viscosity gas. On the other hand, when compressing a gas at lower temperature, below the critical point, we reach the condensation point when we generate a high density and a high viscosity liquid. At above the critical point, heating and compressing allow reaching the same conditions, but without the phase transition. These temperature changes result in the same change in density at a near critical pressure at 100 bar and typical extraction pressure of 400 bar. This change is small near the critical point where CO2 is highly compressible, but larger and high pressure when CO2 exhibits liquid-like properties. This table reinforces the previous picture. It shows the physical properties of liquids, gases, and supercritical fluids close to their critical points and away from the critical point. Reduced pressure equals 1, and the conditions typical used for extraction, reduced pressure 4. Supercritical fluids exhibit liquid-like densities and solvent power away from the critical points, and gas-like transport properties, low viscosity, high diffusivity. These combinations allow that fast extraction processes. Their solvent power can be tuned by changing system temperature and pressure to extract compounds from solid matrices. And the solute can precipitate out by small changes in temperature and pressure. They can be completely removed because they are gases at normal environmental conditions. This snapshot of a molecular simulation exemplifies the special physical and solvent properties of supercritical fluids. Supercritical fluids tend to organize in clusters. Near a solute molecule, large and bluer, solvent molecules form an outer shell. This is associated with a high local density that can solvate solute molecules. Clusters are separated from each other the same and in a typical gaseous phase. They interact loosely, which is associated with their excellent transport properties. The solubility of vegetable oils and CO2 changes markedly with system conditions. At high temperatures, the effect of solute volatility dominates solubility changes. At above the crossover pressure of about 300 bar, the solubility of oil increases with temperature due to the increase in the vapor pressure and volatility of the oil. Below the crossover pressure, the solubility of the oil diminishes because of the reduction in the density and solvent power of the CO2. when going from typical extraction conditions at 60 degrees Celsius and 460 bar, oil solubility is about 10 grams of oil per kilogram of CO2 to a typical separation condition of 40 degrees Celsius and 100 bar. The solubility diminishes 2 orders of magnitude. It is impossible to obtain similar changes in solubility with conventional liquid solvents without an energy-intensive phase change. In a supercritical extraction pilot or industrial plant, the CO2 flows in a cycle. CO2 is stored in a working tank at the saturation condition at the environmental temperature. To reach the desired conditions within the extraction vessel, the CO2 stream is subjected to cooling, pumping, and heating or cooling. Cooling of saturated CO2 avoids cavitation in the pump. Pumping increases the pressure to the extraction level, 460 bar in this case, and the temperature at the exit is adjusted by the second heat exchanger. In this example, compressed CO2 is heated to 60 degrees Celsius. The CO2 stream exiting the extraction vessel with the solubilized oil is decompressed and heated to adjust the conditions in the separator, 40 degrees Celsius and 100 bar, where the oil precipitates out. At these conditions, CO2 has very limited solvent power. To avoid the solute precipitation in the tubing because of the abrupt temperature decrease, the so-called Joule-Thomson effect, CO2 is heated downstream from the expansion valve. Gaseous CO2 is condensed and stored again in the working tank. Makeup CO2 is supplied to the solvent cycle to replace CO2 losses when reconditioning the extraction vessel or removing the oil from the separation vessel. Supercritical fluids have common features that make them attractive of solvents. Physical properties vary in a wide range with small variation in temperature and pressure, especially near to the critical point. Solubilized solute can precipitate without phase changes. In particular, CO2 can extract high-value compounds from natural resources such as aromas. Because extractions are normally carried out at a near critical temperature and the critical temperature of CO2 is close to the typical environmental conditions, most thermolabile natural compounds in the treated matrix and extract are not harmed. Finally, CO2 can be produced at low cost. Required extraction condition will depend on the type of the compounds that we desire to extract. Essential oils from herbs and spices are extracted at near critical point, typically at 50 degrees Celsius and 90 bar for increased selectivity. Lipids, triglycerides, are typically extracted at high pressure, for example, 40 degrees Celsius and 300 bar. Carotenoids are extracted at even higher pressure of 550 bars to 700 bar. And it's possible to make a fractionated extraction of a substrate, increasing the pressure in the stages, starting near the critical point to remove all essential oil before proceeding the high pressure to extract to 6 lipids and carotenoid pigments. Alternatively, the fractionation process can be carried out continuously using a depressurization cascade. In this case, the extraction is carried out at the least selective condition, where the solvent power of CO2 is in a maximum, for example, 50 degrees Celsius and 550 bar, to remove all CO2 soluble compounds. In the first separator, the pressure is reduced from 550 bar to 350 bar to precipitate out carotenoid pigments. In the second separation stage, the pressure is further reduced to 200 bar to precipitate lipids. And the third separation stage, the pressure is reduced again to 60 bar to precipitate out the essential oils and recover CO2 for recycling. Supercritical CO2 extraction of solid substrate is mature technology, and there are many companies worldwide offering extract, obtaining using supercritical CO2 or extraction equipment. This slide shows several companies offering extract from different vegetal substrate. For example, Fladex in Germany, Microalgae, for example, Cyanotech in Hawaii, and Hope Cons, for example, Nateco in Germany. It also shows companies that manufacture supercritical CO2 extraction plant. For example, Natex. And people interested in this information can contact us for more details by email or at the end of this presentation. Make some question about it. Our research has been driven to scale up issues in cases where experimental information is difficult to obtain. We adopted computer simulation as an excellent tool to optimize and cost supercritical CO2 extraction processes. Computer simulation requires robust mathematical models of the CO2 extraction process. Typical model for supercritical CO2 extraction of solid substrate in literature adopt the following simplifying assumptions. Equal size particle of single geometry, spherical. Plug type flow pattern of CO2 within the structure, and constant pressure and temperature within the structure. However, there's experimental evidence signaling the presence of non-idealities in the extraction process at pilot or higher scales. In the extraction of bauxite with CO2 at 40 degrees Celsius and 300 bar, there is virtually no difference in the cumulative extraction curves of the oil obtained at the laboratory scale for the oil at similar but not equal superficial CO2 velocities. However, the cumulative extraction curve obtained in a pilot plant under same conditions and an intermediate superficial CO2 velocity is slower. This suggests that some of the simplifying assumptions listed before did not apply in these experiments. Okay, so two mass transfer models were considered in our work. A rigorous desorption, dissolution, diffusion, or triple D model that considered physical phenomena in the inner void volume of the particles, and a simplified one that neglected this inner void volume. For the extractions, we considered two stages for the extraction. First, an static extraction, and then a dynamic extraction. In the static extraction stage, the extraction vessel with the substrate is pressurized with CO2 up to the extraction conditions, and then the inlet and the exit valve are closed. This contact is kept up to reaching equilibrium conditions of the oil between the solid and fluid phase. And this equilibrium partition is represented by a absorption isotherm isobar that depends on the initial content of content of the oil of the substrate. In our model, we use the continuous function experimentally determined for pre-pressed rapeseeds by Urrego and co-workers in 2012, which is extrapolated to the extraction conditions of even primrose at 40 degrees Celsius and 450 bar. To determine the final solid concentration in the solid and the fluid phases at the end of the static stage, we intersected the absorption isotherm isobar with the mass conservation line for the oil. This red line represents the mass balance in the general case where CO2 occupies space in the intraparticle void fraction, epsilon, and intraparticle void fraction, epsilon sub p. When the intraparticle porosity is neglected, the oil conservation is represented by the red line. Sorry, but the blue line. you can observe that the solute concentration in the solid fluid concentration do not coincide, but the difference for the oil content in the CO2 at the end of the static extraction period for the two models is very small. The model for dynamic extraction stage considers oil content and the supercritical and solid phase. This equation represents the differential mass balance for the oil and the CO2 within the extraction vessel. The concentration of oil in the CO2, C sub F, depends on the time and the axial coordinate. J is the oil flux from the solid substrate to the CO2 phase. U is the superficial CO2 velocity within the extraction vessel that is estimated as a function of the mass flow rate of CO2. The initial oil concentrations correspond to the equilibrium concentration reaches in the static stage. The boundary conditions indicate that pure CO2 is continuously fed to the extraction vessel. Finally, the extraction yield is accounted with a differential equation that sums the oil that exits of extraction vessel with the CO2 extreme. Oil concentration in the solid phase was modeled using the desorption dissolution diffusion model, the hypothesis. Time derivatives consider the average oil concentration in the solid substrate and the CO2 within the substrate pores. J has a negative sign indicating that the oil leaves the particle. It depends on the global mass transfer coefficient, K sub P, and a driving force corresponding to the difference in the oil concentration between the particle pores and the supercritical CO2 phase. In turn, the global mass transfer coefficient depends on a film mass transfer coefficient, K sub F, and the effective diffusivity of the oil in the particle, D sub E. The simplified model does not consider the inner porosity of the substrate. In this case, the driving force for the J term corresponds to the difference in the oil concentration between a fluid equilibrated with the solid substrate and the actual supercritical CO2 phase. The equilibrium concentration in the fluid phase was calculated using the absorption isotherm isobar of Urrego and coworkers as a function of residual oil concentration in the solid substrate. To apply the rigorous triple G model, we eliminated the solid concentration and the network of interconnected pores within the shared substrate by assuming equilibrium partition of this solid between the solid substrate and the CO2 within the pores, given by the absorption isotherm isobar model of Urrego and coworkers. This resulted in this very complex expression for the solid flux. As before, we assumed that the initial solute content in the two phases within the extraction vessel was defined by the equilibrium condition achieved during the static extraction period. Model parameters were estimated or calculated for information available in databases or in literature correlations. The density and viscosity were calculated for pure CO2 using the RefPro program at process conditions. The binary diffusion coefficient of the oil in CO2 was estimated using the correlation of Funasukuri and coworkers as a function of system temperature and CO2 density, and using triolene as a representative component in vegetable oils. Parameters alpha, E, and N from the absorption isotherm isobar model of Urrego and coworkers were estimated as a function of system temperature and CO2 density, and the oil solubility in CO2 was estimated using the correlation of Del Valle and coworkers as a function of the same variable. The film mass transfer coefficient was estimated using the dimensionless correlation of King and Catchpole for a Sherwood number as a function of Reynolds and Schmidt numbers here defined. We compare the best fitting of the general model in thick lines and the simplified model in thin lines to the cumulative extraction curve of evening primrose pellets using supercritical CO2 at 40 degrees Celsius and 450 bar. We used as a substrate pellets of 2.5 and 4 millimeters in diameter, having the height to diameter ratio of 1. A single effective diffusivity was fitted to all which define a microstructural value and inner porosity when using the general model. Both models, the general and simplified models, represent the experimental data well, and there were no significant difference between each other. In this work, we studied 4 non-idealities: extraction of packed bed with a particle size distribution and stratification, radial gradients in axial CO2 velocity resulting from radial gradients in bed porosity, axial gradients in system pressure resulting from the pressure drop of the CO2 along the extraction vessel, and local variations in system temperature, which affects the physical properties of CO2 within the extraction vessel. This slide describes the adaptation of the simplified model to the extraction of packed beds having a particle size distribution. Similarly, we adapted the more complex general model to the same purpose. In this case, the mass transfer flux was a weighted average of the individual fluxes for each particle size fraction. Therefore, the number of particle fractions in the packed bed will define the number of differential equations for the average solid concentration of the solid, global mass transfer coefficients, specific areas, equilibrium concentration in the fluid phase given by the sorption, isotherm, and isobar model. At the beginning of the extraction, here, in initial condition, the average solid concentration in solid phase is the same for all particles, regardless of their size, and equal to the one determined in the static stage. Our results showed that the general model was predictive for the extraction of evening primrose pellets with CO2 at 40 degrees Celsius and 450 bar. These are the same results previously presented when comparing the general and simplified model. The simulated cumulative curves show the extraction of packed beds of single particle size, L pellets for 4 millimeters and S pellets for 2.5 millimeters in the upper curve. Then the extraction of 3 different B-size samples were simulated corresponding to packed beds formed by L and S samples in different proportions: 1:3 green curve, 1:1 red curve, and 3:1 blue curve. The southern mean diameter for each packed bed is reported within parentheses. Comparison of simulated and experimental data highlighted the predictive nature of the model. The extraction of the packed beds was also simulated using a single particle size corresponding to the southern mean diameter. This resulted in a cumulative extraction curves that did not coincide with those simulated considering the particle size distribution and overestimate the experimental data. The simplified model was predicted to describe the effect of substrate stratification on the extraction of packed bed with a particle size distribution. In this example, pellets of cranberry fruit seeds of 2 and 4 millimeters were extracted with supercritical CO2 at 40 degrees Celsius and 300 bar. As before, a single effective diffusivity and oil solubility described the extraction of the 2 substrates. When we then simulated the extraction of 3 packed beds of 1:1 mixture of small and large pellets, first with large particles at the inlet of the extraction vessel in brown, second with randomly distributed particles in pink, and third with small particles at the inlet of the extraction vessel in dark blue. When the simulated cumulative curves were compared with experimental data, we again conclude that the predictive nature of the model. We also compared the cumulative extraction curves of packed beds with a particle size distribution, considering a normal distribution, a positively skewed normal distribution, and a negatively skewed normal distribution, all with the same southern mean diameter. Positively skewed distribution represents the physical case where the packed bed is formed by particles retained by a sieve. This case results in slow extractions. Negatively skewed distribution represents a packed bed formed by particles that pass through of opening of a sieve. This is the case when attempting to avoid agglomeration problems of fine particles within the extraction vessel, and this results in fast extraction. We also compare the cumulative extraction curve of packed bed of particles obtained by fine grinding, narrow distribution, of coarse grinding, wide distribution, with again the cumulative extraction curve did not coincide despite the two samples having the same southern mean diameter. With extraction being faster for the narrow particle distribution that did not have large, slow extracting particles.
This slide shows that as extraction proceeds, the residual amount of an extracted solute diminishes as expected, but that this exhausting depends on the radial position within the extraction vessel, with a faster extraction along the vessel wall than the vessel axis. This is unexpected for a plug flow pattern. Indeed, the flow pattern in a packed bed is not plug type because of a high void region along the vessel wall that resists little to fluid flow. The void distribution across the packed bed is quite complex, however, with several oscillations that attenuate as we move towards the vessel axis. In the present work, we adopted the simplified radial porosity profiles proposed by Fortmeyer and Schuster in 1983 that depend mainly on the ratio of bed inner diameter to particle diameter. As indicated in this slide, we selected parameter epsilon sub 0, the porosity in the bed axis, and C, such that the average porosity corresponds to that predicted by Benaya and O'Neill in 2005 for a packed bed of spheres, and the porosity next to the vessel wall equals 1. These figures show radial variations in porosity for d over dp between 10 and 80, with increased detail close to the vessel wall. We also adopted the radial profiles in superficial velocity in the axial direction proposed by Fortmeyer and Schuster in 1983 that suggest a sharp increase from null next to the vessel wall to a maximal, and then a gradual decrease towards a local minimum in the vessel axis. The velocity profiles also depend on the ratio of bed inner diameter to particle diameter. They include an inner core with plug flow, velocity u sub 0, and an outer annular region that concentrates all variations in axial velocity. The outer annular region is compressed towards the vessel wall as d over dp increases. The radial variations in superficial velocity also depend on the flow regime characterized by Reynolds number. We compute the radial variations in superficial velocity in such a way that the average coincided with the intended average superficial velocity. These figures show radial changes in superficial velocity for d over dp between 10 and 80, and average u equal to 1 millimeter per second, with increased detail close to the vessel wall. As the ratio of extractor diameter to particle diameter increases, the distance to the wall of the central core with constant condition decreases, and the CO2 velocity approaches the average value. For d over dp equals 10, the annular region occupies 1/3 of the distance to the axis of the extractor, and the CO2 velocity in the axis is little more than half of the average velocity. positions of maximum actual superficial CO2 velocity are 1/4 of the particle diameter of the extractor wall. And these velocities vary between 2.5 and 5 times the average velocity. The odds number, which indicates the ratio between internal and external resistance to mass transfer, determines the extent of the influence of radial variations in superficial velocity on extraction curves. As the average superficial CO2 velocity increases, the field mass transfer coefficient increases and the external resistance to mass transfer decreases. This increasing velocity reduces the effect of the velocity profile on vegetable oil extraction as the thick lines for velocity profiles approach thin lines for plug flow. We also increase the odds number by reducing the effective diffusivity of the oil in the substrate to increase the inner resistance to mass transfer. Pressing out more oil in sample pretreatment reduced the internal void fraction of the substrate. The associated increase in the microstructural factor Fm from 5 to 40 achieved the required reduction in effective diffusivity. Overall, the distance between the curves, considering and neglecting the radial variations in superficial velocity, decreases as the odd number increases from 5 to 95, being negligible at the last level. When keeping the odds number constant by changing particle size and average superficial CO2 velocity simultaneously, there was a very complex dependence of the radial profiles in superficial velocity on the extraction curve, depending on the ratio of vessel diameter to particle diameter. However, we made the comparison for a very narrow interval of d over dp between 10 and 20. There was a substantial reduction on the effect of the radial profiles of superficial velocity on the supercritical CO2 extraction of vegetable oil from a pre-pressed substrate as compared to the plug flow conditions, thin lines, when increasing the vessel size from a typical laboratory size of 0.2 liters to an intermediate pilot plant size of 13 liters and large industrial sizes of 100, 100, or 500 liters. In this comparison, all other factors, such as particle diameter, average superficial CO2 velocity, and vessel height to diameter ratio, were kept constants. We proposed the following proxy to represent the extraction with radial profiles of porosity and superficial CO2 velocity in the actual direction in industrial extractors. Extraction in the central core, estimated for epsilon sub 0, approaching the average porosity value, and U sub 0, approaching the average U value, approximates full bed extraction, and the small reduction in oil extraction rate is related to the small decreases in porosity and superficial CO2 velocity in this region, which CO2 can bypass by circulating in the annular region. The substantial differences observed for the simulations in the annular region, highlighted in green, between the actual profiles, thick line, and average values, thin line, agree with the other observations in this part of the study. To study the effect of the pressure in the bed extraction vessel, we're going to switch from the supercritical CO2 extraction of vegetable oils from pre-pressed seeds to that of essential oils from herbs, spices, and other vegetable substrates. The reasons for this will become evident shortly. Budish and co-workers proposed this equation in 1999 for the solubility of orange peel oil in supercritical CO2 at near critical pressures between 70 and 120 bar, and near critical temperatures between 40 and 60 degrees Celsius, typically employed for the selective extraction of plant essential oils. It is evident that the essential oils become fully miscible with CO2 at a temperature-dependent pressure, about 85 bars at 40 degrees Celsius, 100 bar at 50 degrees Celsius, and 115 bar at 60 degrees Celsius. We needed experimental data on extraction kinetics to model using the simplified version of the triple D model coupled with a simple sorption model. We adopted the data of Pollana and co-workers from 1999 on the supercritical CO2 extraction of bergamot peel oils at several combinations of extraction temperature and pressure. Because the so-called pseudo-SIP sorption model requires the solubility of the essential oils in CO2 at the extraction conditions, it is relevant pointing out that the combinations of temperature and pressure used by Pollana and co-workers are below those for mutual miscibility of citrus, essential oils, and CO2. The few combinations of residual essential oil content and operational solubility following the static extraction in symbols bring doubt on the sorption model parameters. We selected N and E values such that the sorption model, the continuous line, approached the linear partition assumption dotted line, typically adopted when applying a linear driving force hypothesis. The application of the simplified triple D model produced a best fit value of the microstructural factor of about 880. This value is much larger than for the supercritical CO2 extraction of vegetable oil from pre-pressed seeds. Bergamot peel pretreatment, consisting of drying and coarse grinding, was milder to take advantage of the microstructural barriers to mass transfer to selectively extract the essential oil from the peels. The top pressure drop estimated using the Ergun equation corresponds to the imminent fluidization condition. Under imminent fluidization conditions, the pressure drop weighted by the cross section of the bed equals the weight of the material loaded in the packed bed, allowing the maximum superficial velocity of CO2 rising along the vessel to be estimated. This figure shows that the pressure drop increases with decreasing bed porosity and particle size. Note that in the definition of Reynolds numbers, the product rho times B is replaced by the mass flow per unit cross-sectional area of the bed G, which remains constant. To decrease the bed porosity to the levels required to increase the pressure drop sufficiently, we assumed that the packed bed was subjected to axial compression to increase the vessel load. The decrease in bed porosity from 0.35 to 0.2 by axial compression collapsed the structure and decreased the internal porosity of the particles below 0.35, a typical value for citrus peels. The decrease in internal porosity was associated with a proportional reduction in particle volume and an associated decrease in the diameter of the spherical particles. The reduction in internal porosity decreased the microstructural value, which decreased the effective diffusivity of the essential oil in bergamot peel oil particles. We compared simulated extraction curves with pressure drop, thick segmented lines, with control curves without pressure drop, thin continuous lines. In a tall industrial extraction vessel, 1 cubic meter in capacity and 3.6 meters in height, we observed the negative effect of a decrease in bed porosity from 0.4 to 0.2 on reducing extraction rate and accentuating the impact of the pressure drop. For a given bed porosity, the negative effect of the pressure drop was accentuated slightly when increasing initial particle diameter from 0.5 to 2 millimeters. For a given bed porosity and particle diameter, the negative effect of the pressure drop on the extraction of bergamot peel oil diminished as the extraction pressure decreased from 100 to 90 bar. Finally, we observed minor effect of mass flow rate of CO2 per unit of the cross-sectional area of the bed on the reduction of the extraction rate of bergamot peel oil caused by the pressure drop of the CO2 in the bed. We studied this effect because the experimental value of the citrus peel density was higher than estimated based on the packing density of the substrate in the work of Poyana and co-workers. This increasing porosity allowed a rise in CO2 velocity without imminent fluidization. This figure shows the increase in extraction time of bergamot peel oil with pressure drop as compared to a control simulation without pressure drop as a function of the variation in oil solubility with actual position along the bed. For comparisons, the extraction yield remained unchanged and corresponded to that achieved following a 6-hour extraction in the system that accounted for pressure drop in the extraction vessel. The abscissa in this graph is the product of the change in the solubility with pressure and the change in pressure with position. The former depends on phase equilibrium, whereas the latter depends on the pressure drop in the packed bed. This figure shows the immense dependency of extraction time on particle size. The extraction time increases by a factor of about 4 in the most unfavorable conditions, related to a reduction in bed porosity from 0.35 to 0.2. There is a general trend for 0.5 millimeter particles in red that is independent of the inlet pressure of the CO2. Also, the pattern for 1 millimeter particles in blue holds out even when the mass flow rate of CO2 per unit of the cross-sectional area of the bed increases. Temperature gradients can be developed in a continuously operating industrial vessel as a result of the pronounced cooling of vessel walls during depressurization due to a Joule-Thomson effect. Temperature gradients appear during the static extraction period as a result of differences in temperature between the vessel wall and the substrate unloaded CO2. The temperature gradients developed during industrial vessel reconditioning cause differences in the temperature of the CO2 stream that leaves the extraction vessel as compared to the inlet temperature of the CO2 stream and that of the extraction vessel wall, adjusted to the required set point value. This figure shows the variations in the solubility of vegetable oil in supercritical CO2 as a function of system temperature and pressure. To study the effect of temperature gradients on supercritical CO2 extraction of vegetable oils from a pretreated seed, we need to move away from the pressure crossover region, or about 300 bar in this case, where there is a limited effect due to the trade-off of solute volatility and CO2 solvent power. Below 300 bar, oil solubility is small. Solubilities are more substantial and positively affected by system temperature above 300 bar. We selected 480 bars for our experimental study and temperatures of 40 and 60 degrees Celsius that caused an increase in solubility by a factor of 37%, from 16.2 to 22.1 grams of oil per kilograms of CO2. When the extractor and its contents equilibrate at 60 degrees Celsius and CO2 is fed at 40 degrees Celsius, there is a vast difference between the temperature at the inlet in green, close to 40 degrees Celsius, and the other positions in the extractor, closer to 60 degrees Celsius. These differences in temperature suggest a swift heat transfer under this heating condition. The pattern repeats when replacing glass spheres with a slightly larger vegetable substrate pellets, but in this case, the approach to steady state is slower, which may be due to the worse transport properties of the substrate than glass. Also, the fluctuations in temperature are higher due to poorer packing of cylindrical substrate pellets than of glass spheres. When the extractor and its contents equilibrate at 40 degrees Celsius and CO2 is fed at 60 degrees Celsius, temperatures distribute more evenly throughout the packed bed, and the approach to a steady state condition is delayed. These trends are possibly due to a worsening in heat transfer because natural convection opposes rather than reinforces forced convection. The two trends, previously established trends are reinforced when applying cooling conditions to an extraction vessel packed with vegetable substrate pellets. To study the effect of temperature gradients on supercritical CO2 extraction of vegetable oil from prepressed cranberry seeds, we performed isothermal experiments. In these experiments, the initial slope of the oil yield versus a specific CO2 consumption corresponded to the thermodynamic solubility of the oil in CO2 at 40 degrees Celsius and 480 bar in blue, or 60 degrees Celsius and 480 bar in red. In the cooling experiment, when feeding CO2 at 60 degrees Celsius to an extraction vessel equilibrated at 40 degrees Celsius, the extraction curve coincided initially with the isothermal curve at 40 degrees Celsius. Later, it deviated positively due to the positive effect of feeding a hotter CO2 stream to the vessel. In the heating experiment, when feeding CO2 at 40 degrees Celsius to an extraction vessel equilibrated at 60 degrees Celsius, the extraction curve coincided initially with the isothermal curve at 60 degrees Celsius. Later, it deviated negatively due to the negative effect of feeding a cooler CO2 stream to the vessel. Overall, the extraction curves in the presence of temperature gradients were determined more by the initial and vessel wall temperatures than the inlet temperature of the CO2, with small deviations being determined by the latter. Future work on this subject will be part of the doctoral thesis of Felipe Toledo. Felipe will develop a model for temperature gradients within the packed bed extraction vessel, accounting for all heat transfer mechanisms, conductive wall-to-particle and particle-to-particle mechanisms, and convective wall-to-fluid and particle-to-fluid mechanisms. Subsequently, he will use the steady state temperature field to predict local variations in physical properties and mass transfer parameters, similar to radial changes in the model without plug flow, and actual differences in the model with pressure drop. Finally, he will incorporate these local variations in temperature to a simulation model for mass transfer in the packed bed extraction vessel, the same as in the case without plug flow. We divide our conclusions into two parts. This first part refers to the findings of the mathematical model used in the various simulations. A distortion dissolution diffusion model with a linear driving force was developed to predictively simulate supercritical CO2 extraction of pelletized oil seeds using the equilibrium partition sorption isotherm isobar of Urrego and coworkers and the oil solubility correlated by Del Valle and coworkers. Mass transfer within pelletized oilseed samples can be accounted for by a particle size independent microstructural factor F sub m, defined as the ratio of the binary diffusion coefficient of the solute in CO2 at extraction conditions, D sub 1, 2, and the effective diffusivity of the solute in the pre-treated substrate, D sub E. A simplification of the rigorous triple D model that neglected the internal void fraction in the substrate was also developed that allowed reducing the computational effort. The second part of our conclusions refers to the non-idealities of this extraction process for solid substrate that was the focus of this research. Extraction curves of substrate with a broad particle size distribution are poorly represented by those of mono-sized substrates having the same Sauter mean diameter. Radial gradients in axial CO2 velocity resulting from an increasing void fraction near the vessel wall reduce cumulative extraction of oil, and this deleterious effect increased as Biot's number decreased when decreasing CO2 flow rate or increasing residual oil content after prepressing, or as vessel size decreased with an associated increase in the D over dP ratio. A proxy to estimate the effect of radial porosity and superficial velocity profiles is the extraction of the central core at epsilon sub 0 and U sub 0. The precision of the estimation improves as the extraction vessel volume increases. Pressure drop negatively impacted supercritical CO2 extraction of citrus peel essential oils at near critical conditions due to the pronounced decrease in essential oil solubility. Temperature gradients affected oil extraction curves from pelletized seeds that was more affected by the temperature of the vessel wall than the inlet CO2 stream. This concludes our presentation. Thank you very much for attending.
Thank you very much for both of you and for sharing your knowledge with us this time. So please, let's start question and answer portion of this webinar. Remember to turn on your microphone just in case you want to ask the question directly to the speakers, or you can also write it down in the chat and I will read it aloud for you. Anyone?
Aquí los acomodamos, no sé, ponle tú de un micro a 100. Y eso
anyone with a question? So, okay, I'll start if no one wants to start. And, oh, sorry, Dr. Jerry King, thank you.
Jose and Dr. Núñez, you modeled for essential oils laboratory data for Polyani over a discrete pressure temperature range, and in the impression I got for the bergamot seed oil peels, was that you were taking data from a non-pelletized system and using your D3 models, et cetera, to modify that. So in the chat, I posed a question: can you use a non-pelletized data and successfully do these predictions on a more ill-defined substrate? And I gave an example of one in my chat. Hopefully you understand what I'm trying.
Do you want to reply, Gonzalo, or I start?
You can start in this time, José Manuel.
Okay. Pre-pressing, pelletizing, flaking, that kind of treatment that completely obliterates the inner structure of a vegetable substrate fits the description of our models better. When you subject a substrate to a mild treatment, such as coarse grinding, you basically rupture only superficial cells, and you don't have free solute, or you have different fractions of solute that are differently bounded to the matrix. So I don't believe predictions will be as good as in the case of vegetable oils when we use the models proposed in this work. Thank you, Jerry.
Was the bergamot seed oil, how was it treated?
No, sorry. You are wrong, Jerry. The data was taken from bergamot peels, and we extracted the essential oils from the peels.
And were they compressed into pellets or treated somewhere?
No. We took the data from literature, and the Poyana and co-workers extracted essential oils from the peels. It wasn't the extraction of the seeds, and those guys didn't focus on the extraction of vegetable oil. Sorry for the confusion.
I think that Budi Irwan Yash has a question. He has his hand raised, but I'm not sure. Buddy?
I don't see a microphone. He has a.
Oh yeah, that's true. He doesn't have a microphone. Okay. So I do have a question. If I'm allowed, like, what is like the minimum data required to make the model work? I mean, what is the minimum inputs and outputs? Like how hard would be to have this data from an actual process in the industry?
Okay. In general, when you fit parameters in a model, you need this at minimum the same data points as parameters that you want to fit first. But in our cases, for cumulative extraction curves, we need a minimal experimental data point to describe very well the diffusion zone, because of this zone maybe and depends on the substrate and solute that we want to extract, is sometimes you dismiss this region because for example, for the oil vegetable extraction, maybe at high pressure this zone doesn't appear. Okay. But when you extract particles were larger diameter, this zone you have to describe very well to fit very well your parameters. So I don't have a number, but typically you have to do extraction by 1 or 2 hours, and this time you maybe obtain 10 experimental point, and that is enough to describe this zone of diffusion mass transfer controlled. Okay.
Thank you so much. And I don't know if anyone has a last question or a last comment for our speakers, because we ran out of time. Have you considered finite element method or analysis for this kind of, well, analysis that you're performing?
Actually, we've developed our own code, and this is using MATLAB for differential equations. We use fairly regular geometries. Typically, we try to reduce our particles to the spheres with the same ratio of superficial area to volume, and there is no any advantages of creating a code that would allow the more precise description of mass transfer for irregular shapes and the like. We have a question by Martin.
Yes, I see the Martin. If you want to unmute your microphone.
Yes, hello everybody. Thank you for your nice presentation. I really enjoyed. My question would be, which main parameters of the model needs to be measured in order to feed the model and to predict some I don't know, development of an extraction process?
Okay. Hello, Martin.
Hi.
And in our case, first we have to define what is the fit parameter, and then depends on the example, but in the mostly we fit the F sub m, a microstructural factor that is a correction factor for the binary diffusion. So in these cases, we have to determine very well our pack bed first. You have to determine the initial concentration of the solid in the solid matrix, and then when you pack these particles in a extraction vessel, you have to determine the porosity of your bed, and indirectly you have to determine the inner porosity and the particles. So that you have to describe very well your packed bed to also the extraction condition, obviously, and mainly in this situation. In one of our cases, we have to fit in for example, the saturation condition because of the some problems in our extract, and our extract may result in a problem with the oil, and the solubility was higher than predicted by our correlation. So in that case, only saturation solubility was as a fit parameter calculated in our model, but also you have to describe very well your packed bed. I answered your question?
Yes, so it means that that when you measure these parameters, let's say because it seems that you don't really need to describe or define your system where you are modeling. So basically, you just measure the properties of the raw material which needs to be extracted. Yep. By the porosity, by the initial concentration of the solute, by the inner porosity, and then you define the extraction conditions and the saturation. So basically the solubility, the solubility of the solute in the CO2 at the conditions of the extraction. Yeah. And then you can simulate whatever size of equipment you want to use, and you can see the differences between the different sizes of the equipment, right?
Yeah, yes. And I forgot something very important. The only thing that you have to take care is that your substrate has the proper pretreatment, okay, to break all the mass transfer barriers. So
Yes.
our pretreatment is pelletized, and the particles, because you form an interconnected network of pores that allowing the solute can be diffused in the inner particle to the bulk of the solvent in this case.
So it's a kind of a cell disruption or this kind of treatment.
Exactly.
Nice, very nice. Yeah. It's really interesting.
Thank you very much.
Thank you very much. If we don't have another question, then I'll thank you, both of you again, Dr. Del Valle, Dr. Núñez, for this exciting talk, and thank you all for participating here with us. Keep tuned, please, and check our website and our Facebook page. We also have an Instagram account for more information regarding our summer presentations. I don't know if you want to add something else, Dr. José Manuel or Dr. Gonzálo.
I just want to thank Tecnológico de Monterrey. It's my second house, I would say. And this initiative is a really nice one. And in this particular case, I had the chance to highlight one of my former graduate students that does most of the mathematical simulation work. I had the chance to see a lot of old friends among the assistants. So I'm also grateful for them to take the time to be with us. And I hope that they write an email to us to tell us how they are doing.
If you are open to receive emails, perhaps you can share it with the audience, because I think they do have some perhaps requests. And I will also post the video. Sorry.
Okay, I'll provide that. We should have put this at the end of the presentation. Is my last name all together, Del Valle?
Sí.
Arroba.
Sorry, I'm writing this in the chat in this section. Okay.
Perfect. Just in case someone else is interested or want to email you directly, because I think some people is asking for the if you can share the slides or the presentation, but that's up to you. And I'll upload the video of this presentation in our official website, which I can also share it in the chat so that you can all join there. And again, thank you so much for being here. Muchas gracias, and see you soon.
Okay.
Yeah.
Bye-bye.
Gracias. Bye.
Muy bien, Gonzalo.
Me parece que ya se fue.
Ya se fue, ¿no? Es que yo estuve, el año pasado estuve con José Manuel haciendo este curso ahí en el TEC de Monterrey.
En el TEC, ya.
Sí.
Pero yo le paso los saludos.
Sí, muy bien. No, bueno, sí. No, fue genial, muy bueno. Sí, muy bien organizado y muy adecuado ahora para estos tiempos.
Sí, sobre todo por eso nos ha permitido tener mucha mayor audiencia
sí.
Y bueno, pues sí, ojalá que sí sigamos con esto. Gracias.
Bueno, gracias.